Hi, my name is Rachel Harvey. Today I will be talking about electron spin and quantum numbers. So first we'll talk about electron spin. Electrons orbit the nucleus, but they also spin along their own axis as they orbit the nucleus. Each atomic orbital can hold two electrons, which pair up within the orbitals. We classify each electron in the orbital as spin up or spin down. This just tells us if they spin clockwise or counterclockwise on their individual axis. Think of it like this. Each planet orbits around the sun, the same way that electrons orbit around a nucleus. But each of those planets has their own axis that they revolve around. This is like how the Earth's rotations cause the different seasons in a year. Just like the sun has multiple planets orbiting it, a nucleus can have multiple electrons orbiting it. We use something called quantum numbers to help explain which of those electrons we're talking about. Quantum numbers are kind of like an address that help us identify one specific electron. The first quantum number we'll talk about is the principal quantum number n. This is like the city in your address. It's pretty general. It describes the basic energy state of a system. The lowest energy orbital is assigned n equals 1. But electrons can be excited by many things, such as absorbing light. This causes the electron to move to a higher energy level, which we call the first excited state, and assign the principal quantum number n equals 2. If this electron were to be excited again, it would go to the second excited state, which is assigned n equals 3, and so on. Each principal quantum number corresponds to an orbital, which is also called a shell. Shells with a lower n value are closer to the nucleus and therefore lower in energy. These excited states with higher values are farther away from the nucleus, and those electrons are a little higher energy. This is a demonstration of the shells. As you can see, the lower values are close to it, but they can be bumped up the next level by absorbing energy. Within each orbital or shell, we can describe properties of the subshell using the angular momentum quantum number, which we call L. This would be like the zip code in your address. It tells us which part of the shell or which part of a city that an electron lives in. L can be any integer between 0 and n minus 1. So when n is equal to 1, the only possible angular quantum number is 0. When L is equal to 0, that means an electron can only occupy the s orbital, which is shaped like a sphere. If n equals 2, the possible values of L are 0 and 1, which means the electrons could be living in the spherical s orbital or the dumbbell-shaped p orbital. The higher energy quantum number L orbitals are D and F, which are shaped like clovers, and some people say they look like dumbbells, like a combination of dumbbells. That's what I think they look like, but people say it looks like a clover, and the F is like two back-to-back clover leaves. So the next quantum number we'll talk about is the magnetic quantum number, or ML. This is like your street name or number. There's lots of different houses on one street, and there's lots of different places for an electron to live within the subshell. This is what ML describes. Instead of a house that a person lives in, we're talking about orbitals that electrons can live in. They're all pretty weirdly shaped, and this is like how everyone's house is different. Each of these orbitals are different, and an electron can live in lots of different places, lots of different fun orbital shapes. And the magnetic quantum number ML can be equal to any integer value between negative L and positive L. And going back to where we started, there's a quantum number that represents the spin of an electron. It's called the spin projection quantum number, or MS. An electron that has spin up is assigned the spin projection quantum number of positive 1/2, while an electron with spin down is assigned negative 1/2. This would be like telling someone your apartment number. It's the most specific of the quantum numbers. All of the quantum numbers are important. You can't find someone's house if you just know their apartment number or just their zip code. And each of these describes something more specific. So you're probably wondering what the heck we use quantum numbers for. One thing we can do is use it like an address to identify which electron we might be talking about. If we're talking about an electron in the third energy level in a p orbital, and it's on the px and it has spin up, we can assign it some numbers instead of that long-winded explanation that I just gave. Another use for quantum numbers is counting the number of electrons in an atom. So let's do some examples and I'll show you how we put these numbers to use. Let's say we want to count how many electrons can fit in the first shell n equals 1. Well, if n equals 1, L can only be between 0 and n minus 1, which means the only possible value in this case is L equals 0. If L equals 0, ML must also equal 0. ML can be anything between positive and negative L, but since there's no such thing as positive or negative 0, the only number that ML can be is 0. And within that orbital, there will be 2 electrons, and one of them will spin up and one of them will spin down, meaning one of them will have ms is equal to negative 1/2 and one will have ms equal to positive 1/2. So altogether, we have only 2 electrons in the first shell. That may seem pretty easy, but when you get into higher shells, there are a lot of electrons in each orbital, which makes it kind of confusing. So we're going to break this down as well. Each orbital can hold 2 electrons, but there's multiple orbitals within each shell. For example, the n equals 2 shell has 4 total orbitals that electrons can occupy. And remember that electrons pair up within an orbital, so there's 2 electrons in each orbital. In the case of the n equals 2 shell, you have 4 orbitals, which means that 8 electrons total can fit in there. So let's use this chart to count how many electrons we can have at maximum in an atom with the quantum numbers 4, 1, 0. We do this by adding up all the electrons below and equal to this set of numbers. You might ask, why do we add the electrons below this and equal to it? Well, in most cases, electrons fill up all the orbitals in one shell before starting to fill the higher shells. Since the higher shells are higher in energy, it costs a lot for those electrons to fill that up if it's not easily available to them. And like us, electrons are lazy. They want to use as little energy as possible, so they will go to the lowest possible place that's open. So we have principal quantum number n equals 4, and that tells us that the first 3 orbitals will be filled. So let's add up all the electrons in those orbitals, which is a total of 28 electrons in the first 3 shells. Now let's count how many can be in the n equals 4 shell. We know that the address of the electron we're looking for has L equals 1. That means an electron can occupy the L equals 0 orbital, which is the s orbital, but there can also be electrons in the L equals 1 p orbital. We have 2 electrons possible in the s orbital, which brings our total up to 30. Our final quantum number is ml equals 0. So we count all the electrons in the ml equals -1 and ml equals 0 levels. Each of those can hold 2 electrons, so we'll add those 4 electrons for a total of 34 electrons maximum in an atom with the quantum numbers 4, 1, and 0. Again, this is the maximum. We're assuming that the lazy electrons do the energetically favorable thing by pairing up before they add into higher levels. You might remember we talked about excited states where an electron absorbs a photon and it jumps up to a higher level, which means there's an empty shell. We wouldn't have the maximum number of electrons. But here we're just going to assume that the electrons were all lazy and did the least amount of work possible, so we have at most 34 electrons that can fit in an atom with the quantum numbers 4, 1, and 0. Remember, each of these 34 electrons has an ms that describes whether it spins up or down. We didn't use it here. If we're going to use our address analogy again, we want to identify how many electrons can live in the whole area and not just which electron is in which apartment number. I know quantum numbers can seem pretty complex at first. Hopefully this video was able to break it down for you. These are my sources if you would like to learn anything else about quantum numbers. And I wish you all the best in your future physics adventures. Thank you for watching. You guys can all do this. Let's go.